Welcome to GEOL 2017 lab series. In this set of labs, we are going to address some of the technical aspects and features that you will need to learn with respect to the identification of rock specimens of various nature as well as minerals. Actually, in the first part, really we deal with minerals and some of the key factors really that are related to the description of minerals. So let's start with the tools. Tools are one key aspect of mineral and rock identification. So whenever we deal with a specimen, we have some tools that we can use. The first one is certainly the fingernail, and then you have a number of additional tools. We had already a discussion about this during some of the first lectures, but yes, we of course now deal in more detail with these tools. So our approach is really to address a mineral by studying the characteristics of the minerals. So the first characteristic is certainly the hardness. How do we assess hardness? We have to scratch the mineral or use the mineral to scratch something else. So quite often the tools that are used to scratch a mineral are the fingernail, the copper coin, the pin wire nail, the knife, and instead often we have other tools that you can use to test hardness by scratching the mineral on those tools, and these are the ceramic plate and the glass plate. So these are the tools really used for hardness testing, including the knife if I forgot about it. So knife is quite hard, between 5 and 6.5, and so it's also pointy. It's quite useful if you have a small specimen and you want to test the hardness. So of course, if you can scratch the mineral with one of these tools, you will know that the mineral has usually a lower hardness. So for example, we talked about phyllosilicates. Sometimes you can scratch them with a fingernail, and that's quite handy because you know it's going to be it's going to have a hardness that is less than 2 or 2.5 roughly. That could be the example of talc. We saw that talc is number 1 on the Mohs scale, so easily scratchable with your fingernail. The same would be true for gypsum. Okay. What else? We have also tools that are used to test magnetic properties. So we have a magnet here, which quite commonly will be useful to differentiate, hematite from magnetite, for example, or pyrrhotite, which is weakly magnetic. So you will feel that the strength of the magnetic field is very strong when you are dealing with the magnet attached to magnetite. If there is no response, so the magnet falls quite often, so it doesn't stay attached to the specimen, well, in that case it's no magnetic, so it could be pyrrhotite, for example, or hematite. We have also other tools. So this one is the acid. This is hydrochloric acid. It's not a pure, I think it's just a small percentage, less than 10%, uses solution of HCl. What is sufficient to essentially react with the carbonates that are in either a mineral or a rock. So if you have a calcite, usually it gives a vivid effervescence. Instead, if it's something else like a dolomite, well, often dolomite doesn't really fizz that much unless you pulverize it and you heat up the sample. So that is a good way to distinguish things. Often you have barite, for example, that is a sulfate of barium, and that doesn't really react with the HCl, but they're very similar to carbonates in a way. And so it's useful to test HCl to differentiate especially sulfate from carbonates, as well as sometimes quartz. You can get milky quartz, which could be similar to a carbonate, although it is much harder, but also it doesn't really react to a HCl. The end lens, it's also a tool that is quite useful. We're going to use a USB microscope in this course because this is an online course, so that will sort of replace some of the usage of this end lens. But certainly, if you are interested in examining your mineral kit as part of this online course, I was saying that as part of this online course, we are using the USB microscope, but that's a tool that you use to magnify things. Here you have hand lens at 10 magnification hand lens. It does the same job. You can use it to actually magnify your specimen and look at small scale features and textures. Okay, so highly recommended to get this, and highly recommended to get the mineral science kit. I will give you some instructions separately on how you can get it through Amazon or other online shops like Walmart. Quite easy. So let's review some other things. These properties usually are used to, of course, identify the correct mineralogy. So this hardness is essentially related to the cohesion of the mineral, so the ability to maintain its structure essentially. So if you have a very weak bonds like van der Waals bonds, we saw those in graphite and also in some of the phyllosilicates, well, in that case the hardness will be much lower because it's easy to break those bonds and essentially destabilize the structure of a mineral. So this has been examined by Moss, and he developed this scale. We have discussed this scale previously in the lectures, but it's worth sort of memorizing the scale and have in mind also the different minerals. So with 10 minerals, you can understand the sort of variety of hardness that we have and the strength of the different minerals. And you see essentially ionic compounds and van der Waals bonds on this side, and here we have the covalent bonds. So the diamond is a good example of that. So it's essentially carbon bonded in and forming tetrahedrons of sort of the same dimension and sort of propagating through the structure of the diamond, and this gives a very strong resistance or high cohesion. In fact, most of the diamond is used in abrasion products, so industrial diamonds, for example, that come from the Argyle district in Australia, are quite often sold to industries that have to actually polish things or in sort of drill bits. For example, in exploration, quite often we have to drill through rock to explore for different types of minerals, so metals, usually precious and base metals, and yet perforation of rock is a very difficult endeavor, and in response to that, quite often we tend to cover the tip of the bits that are used to do this perforation with diamond. So you have tiny industrial diamonds that will cover the drill bit and render it very strong and very abrasive. So remember that you can use minerals as a tool as well. So you have a set of tools, we've seen the tools, but of course if you have, let's say, quartz, which is something that could commonly happen while you are sort of evaluating your specimens, If you have some quartz at hand, it will play the same role as your streak plate. So you can use it to evaluate the hardness of other minerals, because you can scratch with quartz other minerals that you are trying to identify, and this will help you with understanding the hardness, because if you can scratch things using quartz, everything that gets scratched will be in this range of hardness. Okay, so remember the fingernail, the coin, the pin nail. It's important to memorize this order so that you are familiar with the different hardness of the different tools. And so usually the coin and the pin nail are very good when you're trying to differentiate things like calcite and fluorite from apatite, which is usually quite hard, as well as the pyroxene and amphibole, which are not listed in here, but they are really in this range of 5 and 6. So if you can scratch glass with a dark mineral, so ferromagnesium minerals, quite often you're dealing either with amphibole or pyroxene. Okay. Another way in which we can assess minerals is by evaluating their density. Okay, and the density is a very simple formula. Usually we have to estimate the mass of the specimen and its volume, because it's a simple ratio. You divide the mass by its volume, and quite often we use these tools. So we have essentially a scale here that is used to weight the specimen, so you will get a value in grams, and then we have this tool here that allows you to estimate the volume by immersion. So quite often we fill it up with water all through it, and then we immerse the specimen and see the displacement of water that usually grows of a few millimeters, or actually milliliters more correctly. And so you can calculate the difference, and this will be the volume of the specimen. Quite often this is expressed in grams divided cubic centimeter, and it happens to be the milliliters are exactly the same, so you don't need to make any conversion. So essentially 500 millimeters will be 500 cubic centimeters. So that is an easy calculation to make, because you take the mass in grams and you divide it by the milliliters. But remember, you have to calculate the difference when you do that. So by immersion, you will see the change in volume, and that is what should sit underneath this ratio. So that's an approach that is quite commonly helpful, because we can rank by density our minerals. So we'll be in a position in which we can differentiate, for example, sulfides and oxides from silicates. Quite often the silicates are lighter, so they have actually a density that is lower if compared to oxides and sulfides, which are quite often really heavy. One good example of a really heavy mineral could be the galena. Galena is a lead sulfide, and so it's quite often really heavy because of the lead content. Of course, you have to refer back to the Mendeleev table of elements, and you will see that depending on the atomic number, the mass of the atoms gets bigger and bigger. So if you take uraninite, for example, it will be even denser than your galena, because uranium is 238 or more, depending on the isotope you consider, and instead lead will be the 206, 207. So you got a big difference there with respect to density. Okay, so remember, density can be helpful to differentiate silicates from sulfides and oxides. We can now move into the characteristics of minerals. So we are going to look at some of the optical characteristics that are critical for the differentiation and probably are the most important, and as part of this online course they will be quite easy to implement even if you're dealing with either an image or a video of a specimen, because you can remotely, I think, recognize some of these features quite easily. And we will see that in the lab lecture that will be dealing with sort of a tour of the different mineralogical aspects. But let's start with the color. Color is really important, but it can be misleading, so you have to be careful. There will be certain minerals like sulfur that have a quite distinctive colors, but other examples such as this one of the garnet can be tricky, so color cannot be really useful in the recognition of garnet unless you find context for it. But yes, you can see this example here with different types of garnet which have usually different names. This is not really part of the examination. The need here is to recognize garnet in general, so I'm not expecting you to differentiate almandine for spessartine, for example. But this example is useful because it gives you an understanding of how the color can change. So varieties like almandine, which are sort of this deep red, can dramatically change in color if you move into other things like androdites or uvarovites. Why do minerals have different colors? It's because they have a different solid solution. So quite often garnet, we have seen that some minerals can give solid solution, like olivine or garnet itself can have solid solution, in which you have different elements entering the same sites in a mineral structure. So in the olivine we saw that we have a substitution of iron with magnesium. Well, in the garnet is very similar. You will have variety that contain iron that are sort of particularly enriched in iron and give this reddish color. Other variety will have more chromium, and then you have calcium varieties of garnet which are more pinkish in color, and so on. So a number of substitutions will influence the color of this mineral, but how do we recognize it then if we cannot use the color? We will refer to the hardness, the structure, so the habit of the mineral is usually the same, and in response to that you are in a position in which you can recognize the mineral. So color can be useful, but it can be also misleading, so we have to be very careful. The habit of a mineral, so its shape, so the overall shape of the mineral is really important. It does help you a lot, and it is important to be familiar with the basic habits of some of the key silicates as well as some of the sulfides and oxides. So the crystal form and phase is essentially a function of the growth, so how the mineral crystallizes. Quite often you develop nice phases and beautiful crystals when they grow essentially in open space. So often classic geological features that are favorable for the growth of crystals are geopetal structures. So many times we have cavities either in limestone or in other circumstances, even in intrusive rocks. So when you have pegmatites, usually you have a lot of fluids in the magma that tend to create space for crystallization, and so you can develop even crystals like massive amount of feldspar that exceeds, the 100 meters in size, which is quite amazing. And yeah, I think among these features, certainly shape is quite critical in understanding the mineral, or recognizing the minerals that are more critical, really. Being said this, there will be other circumstances in which the mineral will manifest itself without a proper habit. So it will not have a well-defined shape, which is a geometrical shape. Quite often we have a variety of geometries. We'll see some example of those later. But yeah, it's important that we describe well what we see, and cases like quartz could come up, and you might see that the quartz doesn't really have a proper habit, and it's rather forming a vein, or it's actually filling existing space without having a proper habit. This is quite often related to processes such as fractionation. So in a magma chamber, quite often the minerals that fractionate first will be the ones that are euhedral and have a proper habit. So if the minerals have a proper shape, it's likely that they were the first to crystallize. And that's because you do have a competition that takes place in which the force of crystallization is essentially critical in leading to the formation of a crystal. Be really important in this case, because it will allow the crystals to form a proper habit. Quite often also, if there is a lot of competition, so if we have multiple phases that are crystallizing, this is also resulting in smaller crystals, because essentially the space is shared between different mineralogy. These are some of the common terms that are used when you are describing a mineral. In your examination, you will be tested on this type of terminology. So I might ask you if, for example, a crystal of pyrite is acicular or bladed, or if it's rather an equant or stubby habit. So the habit really has to be something you use for the identification of a mineral, and it's important to learn it. So common habits, we have the acicular. Quite often we have amphiboles, so pyroxene and amphibole can grow with an acicular or needle-like habit. Then we have bladed examples, so tabular. So if you take, for example, sanidine, so a variety of high-temperature feldspar, quite often it shows this type of habit, so the tabular or bladed. Other examples, certainly the equant example is the garnet. We saw examples of dodecahedrons of garnet, or cubes of galena, or octahedrons of spinel. Those are the equant or stubby habits. And then we have blocky prisms, which are quite often differentiated from columnar or prismatic prisms. So the blocky is usually representative of minerals such as olivine, or so the monocline or rhombic minerals, and also the feldspars. So tectosilicates will be sometimes blocky, so K feldspar can be blocky. And then you have a nice B pyramid there, so a good example of columnar or prismatic minerals. Quite often we find quartz with that symmetry and habit, so the central crystal here. But also other minerals have similar prismatic habit, and this could be corundum, or which is a cyclosilicate, or another cyclosilicate could be tourmaline. So quite hard minerals tend to be prismatic and have this columnar habit. Other form of habit also will be function on the way the growth take place, and commonly they form also aggregates. So we will find bladed crystals that form aggregates or reticulate textures. So when you have a lot of needles that are sort of intersecting themselves, quite often we have minerals like titanium oxide forming this type of reticulate texture in quartz, for example. So this could be the rutile. So rutile is a mineral that grow inside quartz and form these typical needles. Carbonates can be stalactitic, and this is really linked to the formation of stalactites in caves. So remember that we can dissolve in water carbonate and we can reprecipitate it. And so caves often have stalactites and stalagmites, and so they can have this characteristic morphology. And then we have other phyllosilicates that can take this fibrous and massive habit, and an example of this could be the serpentine. So serpentine, like antigorite or chrysotile, quite often have this fibrous nature, and you can easily break the fibers with your fingers, which is a good diagnostic feature for chrysotile veins. Other aggregates are commonly found in sulfides and oxides. So you can get things like specular hematite or things like pyrote that you will see is looking like a rock composed of multiple facets, and these are shiny facets, so metallic luster is quite common, and it gives this granular massive appearance to the specimen. So the crystals essentially are very tiny, and they form a mass or an aggregate of small crystals. Other minerals such as hematite can form these globular features, and so quite often these are termed bothroidal because of these hemispheroidal shapes that grow, and they are related to the environment of formation. So these are commonly oxidation related features. So in subaerial environment you can deposit hematite and form hydroxides, and these will so like goethite, for example, will tend to inflate and grow, and in response to that you get these bothroidal textures. We saw that some of the phyllosilicates like the micas have one cleavage, and quite often they will be classified for their habit as micaceous or foliated, and that's because you can exfoliate easily with your fingers some of the layers, so the 001 layers of a mica. Lastly, we have some oxides like manganese oxide that can form these characteristic dendritic textures, which are usually formed through self-organization patterns that are related to oxidation, again in a subaerial environment. So often in carbonates you find these characteristic dendrites that are composed dominantly of manganese oxides or hydroxides. So let's see some examples. We were talking about micaceous minerals, so you have an example of a layered structure here in which you get parting into thin sheets. So this is the cleavage I was mentioning. So you can see here crystals really of a muscovite with sort of a classical layer-like or layer cake appearance. So we have several levels or layers that can get exfoliated because of these van der Waals bonds. And yes, if you think about the structure of the muscovite, you remember you have these large cations that can't fit between sets of TOT packages, so tetrahedral, octahedral packages, and this will favor the weakness along a particular plane. Other examples like these fibrous varieties of magnesium-rich silicates are quite common. So we were talking about the antigorites and some of the serpentines will display these classical fibrous features, which is quite distinctive. Again, even these ones are very soft. Remember, the serpentine has that greasy feeling and also is quite soft, so around 2 for most of these minerals, with some exceptions. More massive appearance looks like this dull hydroxide, copper hydroxides could sort of manifest with this characteristic color and also with this massive and dull appearance. And so you have examples of chrysocolla or cuprite that quite often have this massive. Other more classic minerals such as pyrote, quartz could be also manifesting massive appearance. Platy minerals are gypsum. You have, this is a nice specimen. It's commonly called the rose of the desert because it tends to form in aeolic environments, and these are related to the fact that deserts can be quite salty because of the excessive evaporation rate that takes place between night and day, and so you have a lot of salt deposits forming in desertic regions. We will see some examples later when we talk about the sedimentary environments in subca lakes. You can have essentially salt mats forming, and some of these can have these characteristic structures of form tabular crystals of gypsum, which are quite distinctive, and they tend to sort of grow in masses that are quite intricate and show all this complexity. Octahedral is very useful for the identification of spinel. So spinels usually have this characteristic habit as well as some of the sulfides. So remember, here you have a beautiful example of an octahedral diamond, but also very hard minerals such as pyrote ore, also the some of the garnets, some of the sphalerites can have this type of habit, and so that's quite useful. Quite useful as well is the fact that you have these hexagonal sections. So if you have prismatic hexagonal sections, quite often you're dealing with quartz. So you can see here the B pyramid, so at least part of the bipyramid, and also the hexagonal morphology is very helpful to differentiate this mineral from a carbonate. So quite often this will be quartz, and also some of the tabular minerals we saw, such as micas, can have these hexagonal shape, and some of the sections also on the amphibole will be hexagonal or pseudo-hexagonal as well, although the faces tend to have different dimensions in amphibole. But they can be useful for the recognition of amphibole. Granular, as I said, is a speckly, really speckly aspect of minerals, and in this particular case you have these pinkish and bluish colors, which are iridescence colors of a metallic appearance, and these are quite commonly found in bornite. So bornite, which is essentially a copper sulfide, will be characterized by also very tiny crystals and form more massive aggregates. But since you can recognize small grains of bornite, you can call it also a granular texture. And the columnar here is another example. So we have this example of likely sillimanite that quite often form these fibrous textures or acicular textures, and form these agglomerated sets of crystals that are columnar because they are very elongated and prismatic in appearance. Other minerals that grow like this are, for example, the pyroxenes. So you can form pyroxenes such as wollastonite that will have this radiated and columnar habit. Let's talk about another important thing, which is fracture. So fracture can be instrumental in the identification of minerals, because the way a mineral fractures is linked to its structure. Okay, quite often fractures develop along planes of weakness. We saw that for the micas. But fractures can be described and can be identified, and certainly one class of minerals which are easily distinguished are the amorphous minerals. So when you have a volcanic rock, we will learn it down the track, often some of the quartz is crystallized through quenching very rapidly. We talked about that when we were discussing pyroclastic products, and we saw that we can form flamed textures like in the welded tufts, in which you have volcanic glass taking the lead really in these acid magmas. And so often these will be your obsidians, so volcanic glass and vitric quartz, which will have this characteristic appearance. So quite often they manifest this style of fracturing. So you will not see cleavage. We saw that previously quartz doesn't really have cleavage. But if you have a sort of a broken piece of glass in your hands, and it's likely to be quartz, quite often you can see this jagged aspect of the fractures that show also quite distinct curvatures, or like in this specimen of obsidian. So you don't have a planar fracture, the fracture is curvilinear, and this is quite often an indication that you have a conchoidal fracturing. So conchoidal fracturing can be very helpful because it's telling you that the mineral is quite hard, so there is not much in terms of planes of weakness that you can exploit, and so the fractures are quite jagged and irregular. The same applies for uneven fractures. Sometimes the fraction is very irregular in relatively hard minerals that are part of the sulfides. So examples of sphalerite, that in this case is distinguished because of this triangular habit, are quite useful, because you can see all this irregular fracturing is related partly to the cleavage of the sphalerite, but it's quite rough, and it doesn't really show any clear-cut face. So this is another way in which you can define or recognize the mineral. If it does have a rough surface, quite often it can be classified as having an uneven fracture. Okay, and then we have cleavage. Cleavage is really instrumental for the identification of specific mineral groups. So cleavage is helpful if you look at the angles. So usually we can have situations in which we have more than one cleavage. So forget about the muscovites. Think about things like feldspars or carbonates or pyroxene and amphibole. So all those silicates will be significantly discerned from themselves by using cleavage. Cleavage surfaces will be relatively planar and smooth, so they can be recognized because they usually are looking like a face on the crystal. And in fact, you can expose faces of crystals through deformation. How do you tell that that's cleavage? Usually you have multiple planes that are parallel to each other, so you have multiple. We saw that for the muscovites, you tend to form those layers, and they are all repeated in space. And so repetition is certainly a good way to tell apart cleavage from other types of fracturing that occurs in a mineral. So they form in a plane of weakness in the structure of a mineral, where there are weaker bonds in certain directions. We saw that for muscovite or biotite already. But if you look, for example, at the feldspar, usually it forms those classical steps that show the cube. Or take galena, for example. Galena will show similar type of cleavage, so a minimum of 3 cleavages are apparent, are part of the characteristic structure of the crystal. So crystal faces and cleavage faces may be difficult to tell apart, and that's obvious. They are essentially part of the same morphology and structure, and so in some cases it will be impossible to differentiate them. But if you can see the faces of a crystal that are well developed, like in quartz, and inside you find or a feldspar, and inside you find repetitions, you can identify the cleavage quite easily. So quite commonly you look inside the crystal, not on the boundaries, to identify the cleavage. So sections through the mineral can be helpful to do that. Here is an example of cleavage. You can see the internal part. So you have here a face, and if you look at the face of the crystal, you can see lines through it with different orientations, but mostly at 90 degrees. So this could be an example of halite or feldspar, and yeah, this is like forming a step structure. And so when you see steps like this, quite often these are inside the crystal, and those will be classified as cleavage. Faces, well, if you don't have cleavage like in a quartz crystal, you automatically know that those are faces, and if they form hexagonal shapes, well, that's quite commonly the habit of a prism of Druisa quartz, So that's certainly easy to recognize and tell apart from cleavage, and also it doesn't really repeat inside the crystal, so it's much easier to define this as a face. So in summary, cleavage planes are often repeated like a series of steps, and crystal faces are single surfaces. They have no repetition of the crystal face within a crystal. But that's partly true, because even these will have faces, okay? But yeah, you can say this mineral has cleavage and this mineral has no cleavage, which is the most important thing, because cleavage is diagnostic. How is it diagnostic? Well, you can count the number of cleavages you can recognize. So we have different examples here. We have one cleavage, quite commonly I saw muscovite or biotite having this feature. And then we have two cleavages, so the feldspars. Then we have three cleavages. Let's think of, again, other things. Now this would be more the pyroxene and amphibole, and this instead would be your feldspar, because feldspar has three cleavages. And then you have other things like carbonates here, but they have different angles. See how here we have 90 degrees cleavage, and here we have a different angle. So we do have like an orthorhombic shape, and so in this particular case the cleavage manifests itself with different angles, not strictly at 90 degrees. So it can be less than 90 degrees, and so that's diagnostic again. So if you have to distinguish between a feldspar and a carbonate, you could look really at the angle of the cleavages, if you can see the cleavages in the crystals. And then you have even higher numbers of cleavages, and these quite often are found in your sulfides and some of the silicates like garnet. So in this particular case, 4 cleavages can be identified by looking at different faces and sort of evaluating the position of the cleavage planes. So if you can identify that there are different cleavage planes and you can count them, then you will realize you have more than 3 cleavages, especially in an octahedron like this. The most important example probably for the classification of minerals is certainly in the evaluation of a pyroxene against an amphibole. So we were talking about the angle of cleavage. So quite often we have the classical cross section of a pyroxene will be fairly squared, and you will recognize inside the pyroxene diagonal patterns of cleavage. And so the bigger face usually are at an acute angle with respect to the cleavage, which is important to learn. And these cleavages form a characteristic angle, so they form 93 and 87 degrees, so they are approximately at 90 degrees, and that's characteristic really of pyroxene. If you work through an amphibole, you get similar feature. So the cleavages usually form acute angles with the big faces. So you can recognize in this section there are small faces and big faces. So you have your cleavage inside the section of the crystal, and you can see this hexagonal basal, pseudo-hexagonal, because it doesn't have, the same length for the sides here, but still you can count 6 faces. But at the same time it's interesting because the angle is much smaller on one side, and so you have a 5624 degrees relationship, which form these features that are essentially losange shaped. And so losange sections quite often, or rhomboedral sections, or rhomboidal sections are a characteristic diagnostic feature of amphibole. So important to remember this difference in the angle of cleavage for the differentiation of ferromagnesium minerals such as pyroxene and amphibole.